Okay. In the first question, we will do a hypothesis testing based on a normal population and the variance is known. So the question is, supporters claim that a new windmill can generate an average of at least 800 kilowatts of power per day. Okay, so our mean is known. It is here. Actually, this is H0, okay? This is a claim. And daily power generation for the windmill is assumed to be normally distributed. Okay, we know our standard deviation. This is a fact, okay? This is a claim, and this is a fact. And we take a sample, our N is 100 here. And the alternative hypothesis is true mean is less than 800 kilowatts. Okay, so in this question, we will find type 1 error and type 2 error. First of all, let me remind you that type 1 error is rejecting H0 incorrectly. I mean, your claim is true, actually, but you still reject it. Okay, the reason is here, I wrote it in detailed explanation. To commit a type 1 error, X bar we find from the sample should be less than 776. Okay, this is the decision criteria. It is given in the question. And by just bad luck, we take many small values from our sample, okay, from our population. Our sample includes small values. Actually, our mean is 800, we assume that. But when we pick samples out of this population, we are constantly picking these values, okay? Small values. So by just bad luck, I guess, we have a sample mean smaller than our true mean, okay? So this is the type 1 error. In order to find it, we are writing the decision criteria first. The decision criteria was if our sample mean is less than 776, then we were going to reject this hypothesis, okay? So the probability of committing a type 1 error is basically probability of X bar is less than 776. So now we need to normalize this thing to use the Z table, okay? So from both sides, we are subtracting the true mean and then divide this thing by our sample standard deviation, okay? Here in this question, we know the population variance, population standard deviation, and since we're dealing with X bar here, sample mean, we need to use sample standard deviation. And we know that sample means standard deviation is this, okay? Actually, this is not sample standard deviation, it's sample means standard deviation, okay? So we are just putting the values now here. This left-hand side, since we normalized it, has become a Z, okay? And the right-hand side, we have written this 776 and then subtract the true mean and divide this thing by the standard deviation of sample mean, and we get this, okay? Probability of Z is less than -2. And we're just looking at the table right now. So we're finding the probability 0.0228. So this is the probability of committing a type 1 error. This is alpha. Okay. And in the part B, now we are going to find a type 2 error, probability of type 2 error. Type 2 error is you don't reject a hypothesis despite it is wrong, okay? Now we are assuming that the true mean actually is 740, but we will have a sample mean greater than 776, and thus we won't reject, okay? But actually it is wrong. Okay, RH0 is wrong actually, but we won't reject it. So how can we do that? We are writing the criteria again. Our sample mean should be greater than 776 in order not to reject the hypothesis. So we are normalizing this thing. We are subtracting the mean and divide the sample mean standard deviation. And then we get this inequality. Now here, when we do the simplifications here, we are seeing that we're asked probability of Z is greater or equal to 3. And this probability is, just by looking at the table, is 0.0030. Okay, so this type 2 error is actually worse than the type 1 error. Okay, so that's why we're using the power of test is not committing it. Okay, power of test is basically probability of not committing a type 2 error. So we are just subtracting this thing from 1 because the whole probability is always 1. 1 minus 0.0013 is equal to this thing. This is the power of test. Do you have any question here?
No, John, I have no question.
Okay. Now, in the question 2, we have two populations. Okay, we take samples from each of them. And the first sample includes 12 values. The mean is 13.8. Standard deviation is 1.2. And from the second population, we take a sample consisting of 15 values. And the mean and standard deviation are different from the first population. Okay. I must remind you that these standard deviations are samples standard deviations. Okay. In the question, we're given that the variances of the populations of the two populations are the same actually. Okay. But in samples, standard deviations change in this question. So we're asked to construct a 95% confidence interval for the difference between true average heights of the two kinds of circus trees. Citrus trees. This is wrong. Okay. Now we are going to deal with the differences between means of the two populations. Okay, we have the values here, and then here we are going to use the pooled variance formula. Why? Because we know that actually the two variances of the populations are the same, but we have two different sample standard deviations. So in order to make these two something useful, we are going to use a pooled variance. It's like a weighted average of them. Okay, the formula is as it's in here, n1 minus 1. Here is our n1, is 12, and the sample variance plus n2 minus 1, which is 15 minus 1 here, and the sample variance of the second, which is given its square. Okay, this is standard deviation, but the formula includes variance. And in the denominator, we have n1 minus 1 plus n2 minus 1. n1 plus n2 minus 2, it means. So this is the formula. We are just putting the values here, and we're finding that our pool variance is 1.8936. Okay. Now, the confidence interval formula includes this. Okay. we need to find an interval which the difference between the true means can be, okay? And it is the samples means differences and plus minus our pooled variance times the kind of weighted average of our sample sizes times our t value. And here we're going to use t value with these qualities, alpha over 2, n1 plus n2 minus 2. Okay, now from now on, we are just going to put in the values. So this is basically a formula using question. That's all. Actually, this topic is mainly formula using topic. Okay, so we're just putting the values. We have found SP, pooled variance here. Here, we're going to write it. And N1 and N2 will come in here. So in this part, we're going to find 0.73. And the T value, you know, our alpha was 5%. Okay, because we are constructing a 95% confidence interval. So our alpha is 5%. It is the probability of making a mistake, okay? 1 minus 95% confidence interval. Our alpha is 5%. So in the formula, since here we're using a two-tailed test, what does two-tailed mean? I mean, we are calculating both the left and right-hand side, okay? So the summation of the left and right will be 5%. So here we're going to use T 0.025. Okay, that's why it's alpha over 2. And the degree of freedom is N1 plus N2 minus 2. Okay. Again, we are checking the T table here. And then we're finding the T value as 2.06. And about this difference of the sample means part, we're finding 13.8 minus 12.9 is 0.9. Okay, they are given also. And then the confidence interval turns out to be 0.9 plus and minus the multiplication of these. It is 0.9 plus and minus this amount. Okay, so when you subtract this value from 0.9, you will get this. And when you add these things up, you will get this. So this means the true means differences is this and this in this interval. Okay, mu1 can be greater than mu2. That's why we get a positive value. And mu1 can be smaller than mu2. So that's why we will get a negative value. Okay. And remember here that in the beginning of the question, we assumed that these populations have equal variances. Okay, now in the part B, we will gonna use this this thing. I mean, we're not gonna use it, but we'll see that this assumption holds. Okay. In the part B, we're going to construct a 98% confidence interval, but for ratio of the variances. Okay. In the first one, we had done the difference of means, and now we're doing the ratio of variances, and it is also a formula, which is as it's in here. Okay. Now the ratio of the variances can be and have to be with 98% confidence level between these values. Okay, now here first we're going to find our alpha, which is 0.02, 1 minus 0.98. Okay, this is our alpha. And we're going to use in the formula alpha over 2 from the same logic here. Okay, it's a 2 there. And then you're writing the actual values instead of the formula. You need to memorize this formula. In the left-hand side, we have the first one's sample variance divided by the second one's sample variance. So we're putting the variances, okay, that they were given in the question. And we're going to multiply it with an F distribution, F value. And we have this information here. Our alpha over 2 is what? 0.02 over 2, it is 0.01, okay? And N1 minus 1 is 11, and N2 minus 1 is 14, and we are looking at the table here, okay? And when we look at table, we are finding the value is 3.86. And the right-hand side, again, we are using the ratio of sample variances, and then we are going to multiply not by 1 over F alpha over 2 and 1 minus 1 and 2 minus 1, but F alpha over 2 now and 2 minus 1 and 1 minus 1. You see the order is changing here. At first, we have 1 over this F alpha over 2 and 1 minus 1 first. Okay, now we have N2 minus 1 first. Okay, these things change. And then when we look at the table, in the table actually in the auto class, we don't have the value for this F alpha over 2, 14, 11. But we have 15, 11 and 12, 11. And values were 4.25 and 4.40, and I took a value in between these things, and I wrote 4.3. Okay, so I just used the formula, and then I have found that the ratio through variances of the two population is in between these values. Okay, now I have mentioned that the question involves this assumption, equal variances, okay? Now, we constructed a ratio of variances interval, and here we can see that 1 is in the interval, okay? So there is no need to reject the assumption. That's the little thing that we should pay attention, okay? It is not necessary, but I'm just saying. Okay. Now, in the question 3, when a process producing ball bearings is operating correctly, the weights of the ball bearings have a normal distribution with mean 5 ounces and standard deviation 0.1 ounce. Okay. And then an adjustment has been made to the process, and the plant manager suspects that this has raised the mean weight of ball bearings produced. Okay, so the manager claims that now the population mean is greater than 5, okay? Initially it was 5, and they have done something, and the manager thinks that now the mean is greater than 5, okay? This is a claim, this is H0. The manager's claim is H0. And he thinks also the standard deviation unchanged, okay? So we still have the 0.5 standard deviation. And we take a sample of 16 ball bearings. And the mean weight is found to be 5.038 ounces. Now, we need to test the H0 and H1. Okay, H0 is pi, and H1 is the manager's claim, okay? So So we're gonna test if if the mean stays the same or not. Okay. So what do we do? Our x bar from the sample is 5.038, and the decision criteria here is basically when we normalize this x bar, we should have a greater value than z 0.05, okay? And the z 0.05 is something you should know by heart, is 1.645. This is a decision criteria in this type of questions. So we are just normalizing this thing with respect to H0, okay? H0 claims that mean is still 5. So we are going to subtract the H0 from the value of the sample mean and divide this thing by the sample mean standard deviation, which is the population standard deviation over square root of our sample size. When we do the calculations, we're finding that 1.52 is less than 1.645, okay? So the critical value we have found is less than, the value we have found is less than the critical value. So we fail to reject, okay? So we can say that the mean is still 5, okay? So manager can't prove that the mean has increased. We fail to reject that mu is 5. And in the part B, we are going to find the probability that H0 actually, this question is wrong, okay? I assumed something else. Okay, we're going to find the probability of the true mean is 5.05. So in this decision criteria, we will reject H0 if x bar minus the mean over the standard deviation of sample mean is 1.645, okay? And this is basically, we can write it in a different way, like we are trying to leave the x bar alone here. And we can say that we will reject H0 when x bar is smaller than 5.041, okay? So here we will accept H0 if x bar is greater than 5.041, okay? We are just gonna use this and turning it to this. And this will be a type 2 error. Why? Because the true mean has changed here actually. The true mean is, we're assuming that true mean is 5.05, but we are not rejecting the hypothesis, okay? So this is a type 2 error. We are finding the probability of x bar is greater than 5.045. So we are just normalizing it using the true mean now, because we're assuming that the mean is 5.05. And then when we subtract the mean and divide the standard deviation of sample mean and do the same thing in the right-hand side, this part has become a standard normal distribution, okay, z, and it is greater than, do the calculations here, it is greater than minus 0.36, okay? Now we are looking at the table and finding that the probability of committing this error, type 2 error, is 0.64 approximately. So the power of the test in the part C will be 1 minus probability of type 2 error, which is B, is 0.36 approximately. In the question 4, we have a normal distribution. We have our standard deviation. And we want to test H0, mu is 20, at a significance level, alpha is 0.05. Okay, so this is a 95% confidence rate. So here we don't know the decision criteria yet. This is kind of a different question. Normally, we were writing, we are going to reject H0 if X bar is greater than something or less than something, okay? But here, we don't know the thing here. The K, I have written the K. I wrote that we are going to reject H0 if X bar is greater than K, okay? But now, in order to find K, we have another kind of information, which is the confidence level. We want it to be 0.05, okay? So here we can normalize this inequality by subtracting the mean, which we are given in the question as 20, and then divide both sides by the standard deviation of the sample mean, and we can equate this probability to 0.05. When we do that, we can use the fact that probability of Z is greater than 1.645 is 0.05, okay? Why? This is from the table, and this is something we should know by heart. This is if this is a standard normal distribution, then you know that mean is 0, and when our Z value is 1.645, the probability left on the right-hand side is gonna be 0.05, okay? And same thing for the left-hand side, minus 1.645 is leaving its left-hand side with 0.05 probability. So we are just equating this Z is greater than this calculation here is 4 times K minus 20 is equal to 0.05, means that this part, 4 times K minus 20, is 1.645, okay? And from here, we are finding the K value, which is 20.41 approximately. So now we can write a clear version of our decision criteria, which is we reject H0 if X bar is greater than 20.41, okay? Now, here we are dealing with a type 2 error, which is being unable to reject the null hypothesis when it is actually wrong, okay? So in order us to not reject the null hypothesis, here you see we reject H0 if X bar is greater than this thing. So we don't reject it if X bar is less than this thing, okay? So we only need to find the probability of X bar is less than or equal to 20.41. In order to find this probability, what are we going to do? We are just going to normalize this inequality. Instead of X bar, we are turning this into a Z. So we are just subtracting the mean and divide it by the standard deviation of the sample mean. But remember that in the question, our alternative hypothesis was the mu is 21. So in this question, we are assuming that the true mean is actually 21, okay? Because we are trying to find the probability that we are wrong about the mean, okay? So actually, we are assuming that the true mean is actually 21, but we are not rejecting the H0 and committing a type 2 error here. So here, instead of the true mean, we are writing 21. And this calculations gives us the probability of z is less than or equal to minus 2.356. Okay, and in the table we can see that this value is 0.0091. This is the probability of committing a type 2 error. So the power of test is probability of not committing a type 2 error is 1 minus r beta here. It is 0.99 approximately. So the power of test is really high. Now we are going to do the same thing, but the alternative hypothesis is changing in part B, which is mu is 19 here. First, like in the previous example, we are writing x bar is less than c. Now we are writing less than c, okay? Because h0 was mu is 20 and h1 was 21 in the first part. So in the alternative hypothesis, since we have a bigger value, we have written the decision criteria in the part A as reject H0 if X bar is greater than K, okay? Because the alternative was greater than the H0. But now in part B, we have a smaller alternative hypothesis, which is 19. So in part B, we are rejecting H0 if X bar is less than some value C, okay? Now, we are trying to find this C value. First, we are going to normalize it, X bar minus mu over standard deviation of sample mean, and we are doing the same thing in the right-hand side, and we are equating this probability to 0.05, which is given in the question. This is the confidence value that is asked in the question. So we know that this 0.05 probability will come out when we are at minus 1.645. Okay, it is the same in the right hand side. This is 1.645. So the probability of X bar is less than minus 1.645 is 0.05. Okay. We have found this thing in the first part in here. Okay. Now all we need to do is from this equation to finding the C, and we're finding C as 19.589. Okay. Now we can find the probability of committing a type 2 error again. So in order to commit a type 2 error, we must be unable to reject the null hypothesis, but in fact the null hypothesis must be wrong. Okay, so in order to not reject, X bar should be greater than C value we have found here. Why? Because we were going to reject H0 if X bar is less than C. So if X bar is greater than C, we won't reject it. We are writing the inequality here and normalizing it with the true mean being 19. So we are finding the inequality as probability of Z is greater than 2.356, okay? And here you see, actually we have found the same probability. It is the same beta again, and the power of the test is the same. About the question 6. Okay, we are thinking about possibility of a ship collision. We're dealing with ship traffic. Okay, number of ships passing the internal program. Sample. Okay, we are dealing with number of ships. This is our random variable here. The number of ships is x. Y, let's say y, because it is y in the question. And the sample mean we have from 60, okay? Sample mean is 7.2 and sample variance is 8.8. And we are trying to construct a confidence interval with 95% confidence, okay, in a one way. So in this question, unit 6. We passed the question 5. Okay, let me come back to it in a minute. Okay, so we have a sample mean and sample variance, and we know the alpha is given in the question. We are asked to find 0.05 confidence level. Okay, so in order to construct the confidence level for the sample mean here is the population mean here is sample mean plus minus our formula. Okay, the formula includes two things basically. The first one will be the critical value for z, which is alpha over 2 equals to 0.025 here. So this is 1.96 from memorization just, okay? And then here we are doing a usage of our given data to construct the variance for this population parameter, which is basically the standard deviation of the sample, okay? And then the sample size. We don't have anything else we can use in this question. So we are using the sample standard deviation and sample size in order to find the variance. And we have used the critical value alpha over 2 here. And then we have found the number of ships, the true parameter, true mean, is going to be between 7.2 minus this thing and 7.2 plus this thing. Okay, so we are just constructing the confidence interval as this, and we can say that I am 95% confident that the number of ships, the average number of ships will be between these values. And in the part B, we have now two different samples, okay? In the winter and summer, the number of ships that are passing through this shore, I guess, changes. So we have two samples here. And we're asked to find the difference in the number of ships, okay? Difference in mean density of ship traffic. Now here, first, we are writing the difference in sample means, okay? They are given in the question. And then we need to have a variance here because, you know, true parameter can differ from the sample data. So what do we write? Since the confidence interval is 95%, our alpha here, I'm sorry, 90%, it asks. So our alpha is 10% here, and we're going to use alpha over 2 from the formula. So alpha over 2 will become 5%. And Z5%, Z0.05 is 1.645, as you should know by heart. And we are going to multiply this thing with what? Since we have now two different sample variances, we are going to take the kind of an average, weighted average of them, okay? The first sample variance over the size plus the second sample variance over the size, and we take the square root of it to find the pooled kind of standard deviation. Okay, now we are putting the values here. 7.2 minus 4.7 is the difference between sample means, and we have a plus minus this critical Z value times our kind of average variance, okay, using different sample variances. And then when we do the calculations, we are finding that the difference between true means can be between this and this with 90% confidence level. So that's all. And let me turn back to question 5. We haven't done it. Okay. Now we have 50 male students who participates college athletics more than the other group, okay? The mean of weight of these students is 68.2, and standard deviation is given here. And we have another 50 students, and these 50 students show no interest in college athletics, okay? And they have a mean mass of 67.5 kilogram and standard deviation of 2.8 kilogram. So the H0 here in this question, actually we are trying to prove that these two different groups have no differences in their mean weights, okay? We are trying to prove that in this question. And then we're writing the null hypothesis and the alternative hypothesis. Let's assume that the null hypothesis is the mean of the first group is equal to mean of the second group. I mean, participating in college athletics doesn't affect your mean weight, okay? This is what we're dealing with. Now, we are trying to actually say something about the differences in their mean weights, right? So I have turned the null hypothesis into this. The mean of the first group minus mean of the second group is 0. There is no difference, I'm saying. And then about the standard deviation here, again, we are using this weighted averaged standard deviation. How we know the standard deviation of the first sample and standard deviation of the second sample here. And then we are just gonna square them because we need variance in the formula and divide them by the sample sizes and then take the square root of it. And when I use this formula, I have found that the standard deviation of the sample means differences is 0.53, okay? Now here we have this decision criteria. Since we are dealing with this thing, we are just, normalizing it. But basically, we are not doing something different. It's actually the thing we are dealing with, which is mu1 over mu2 here, minus the null hypothesis statement, which is 0, over the sample standard deviation, right? Since we have two samples here, and we are dealing with the differences of them, we are using the standard deviation of these two values as it is given in this formula which is found 0.53. Okay. Now, the decision criteria is here. The thing I have written is the same with this thing, minus 0. We don't need it. So we are going to reject the null hypothesis here if this value is greater than z 0.05, which is 1.645 by heart. You need to memorize it. So let's check if it is actually greater or less than the 1.645. We are putting the values for x1 bar and x2 bar, and we are dividing this thing with the standard deviation of the differences of sample means, which is 0.53. And this is giving us the value 1.32. And we know that this is less than 1.645. So we are not rejecting. We fail to reject H0. So we can't say that, oh no, they are different. They are not the same. We can say that. We are unable to reject it. And in the part B, it asks us what should the sample sizes be for us to reject the null hypothesis. Okay. Now, since they are the same sample sizes, the two samples have the same size, 50 and 50 in the first question, then let's assume that the sample sizes we will have in the part B will be the same again. So N1 and N2, okay? We are writing just N because we are assuming that they are equal, just as in the part A. And then here, we don't put in the N value we are given in the question. You see, here we put the values, but now we are not putting the values in because we want to find that value. Okay, we don't know it. We are trying to find this. So we are calculating the sample standard deviation. Sample means differences standard deviation as this value. We don't know the N now. And we need to find an N value which gives us a greater value than 1.645 when we put it in the formula. Okay. You see, if this thing is greater than Z 0.05, we can reject it. So instead of this, I am writing this, and the sample means doesn't change. Sample means don't change. And I am finding this inequality here. The left-hand side includes an N, and if it is greater than 1.645, I'm going to reject it. And the question wants me to find an N value which helps me reject the null hypothesis. So I'm just leaving this N thing alone. And, the 3.75 in the denominator went to the upper side. And, this difference, I divided the both sides with it. And, it came here. And then I have found this inequality. Square root of N is greater than 8.81. Now, we can say that by taking the square of both sides, N is greater than 77. So if N is greater than 77, I can reject the null hypothesis. You see, the sample size really matters. And that was the first part. And the significance level changes in the second part. Now we need to use the 1% significance level. And then, we are rejecting the null hypothesis if this inequality holds. In the first one, we were using the Z 5%, which is 1.645. Now we are using Z 1%, okay, which is 2.33 approximately. Okay. Now again, we are putting the values, but we are not putting any n value because we are trying to find it. And then we are leaving this n thing alone. So we are finding the inequality as square root of n is greater than 12.48. If square root of n is greater than this value, we are able to reject the null hypothesis. So taking the squares of both sides, we are finding n is greater than 156 at 1% significance level. So here you must recognize that as you decrease the significance level, I mean, this is actually increasing the significance level because this test includes 99% confidence level. Okay, so that's why we need a greater n here to reject the null hypothesis. Okay. And the question 7 includes an exponential distribution. Okay, our H0 is theta is 2. Theta is the mean of the exponential distribution here. So we are writing the exponential distribution's PDF in the form of 1 over theta, okay? 1 over theta e2 minus x over theta. This is the PDF of exponential distribution with mean theta. And H0 is theta is 2, and H1 is theta is 5, okay? And the decision criteria is given in the question, which is this. This null hypothesis, theta is 2, is accepted if the observed value of the random variable is less than 3. I mean, if our x is less than 3, then we are accepting theta is 2, okay? Now, in the part A, we need to find a type 1 error, which is failing to reject the null hypothesis when it is wrong, okay? So we need to find an x less than 3, but our actual theta should be 5, okay? So in order to do that, in order to find this probability, what are we going to do? Okay, we are going to reject the null hypothesis when the value of random variable is higher than 3, okay? Because we are accepting it when it is less than 3. So we are rejecting it when it is higher than 3. So probability of, I have written x here, but this is y. You can think of it as x as well. Anyway, so probability of our random variable's value is greater than 3 when our theta is 2, okay? So here we are just calculating the probability. We are writing the PDF here, and the boundaries is what? Probability of y is greater than 3 is the integral thing of PDF from 3 to infinity, okay? You know, this is your PDF, and you are calculating the probability from 3 to infinity. So when you calculate it, you are finding E2 minus 3 over 2, which is 2.22 approximately. So this is the probability of committing a type 1 error, okay? Rejecting the null hypothesis when it is actually true. This is type 1 error. And then we are calculating type 2 error, which is not rejecting the null hypothesis when it is actually wrong. In order to null hypothesis to be wrong, our theta should be 5, but we should be unable to reject it, okay? So we are going to accept the null hypothesis because the value of the random variable is less than 3. So now we are setting the integral from 0 to 3. Here, we are trying to find this probability now. From 0 to 3, and we know that our null hypothesis is wrong. It is not theta is equal to 2. It is actually 5. Okay, so instead of theta in the PDF, we are writing 5 now and calculating the probability by just taking the integral. And it is, you know, the integral of e2 minus y over 5 over minus 1 over 5 comes to the top, comes to the numerator, and these are cancels out. We have minus sign. And then we are putting the values, and we are finding the probability of committing a type 2 error is 0.45 approximately. That was all for this week. You have come out from the midterm recently. I know that. You still have time to study all of these. I don't know if you have finished the topic yet, but you will understand. These are all formula, basically. Do you have any questions?
Jim, I actually have one question about question number 2.
Question number 2.
Go back there.
Okay. Mm-hmm.
There was a calculation, and I was wondering, you know, where f of alpha over 2, where was that part? I think a bit lower in part B.
Yes, f is used when we are calculating the ratio of the variances.
Yeah, okay, here.
Yes, this formula.
Like you see the value 1 over 3.86, like
Yes.
it's the left part of the inequality, and like 4.3 we got, right?
Evet, yes.
So like, how are those different in the formula? Like I see there's n sub 1 minus 1 and n sub 2 minus 1. And on the right side, it's like n sub 2 minus 1, like the opposite, right? But I wonder, how do we get these values different if they're kind of the same? Am I wrong?
Actually, I see your point. Yes, there is this topic when you you can turn this thing into something like that, right?
I guess.
Yeah, you say that this and this should be equal to each other.
Not exactly, but I wonder, why are the values different?
Well, here I have just used the formula, and I have looked from the table, you know, for f alpha, what was the alpha? F 1%, 11 and 14 from the table, and I have seen this value, and then I checked the f 1%, 12.
Okay, those are
and
from the
11.
table, right?
Yeah.
Okay.
Yeah, I have looked from a table, and this values are different from each other. But I remember there is something like that, 1 over f, if alphas are the same, but if you change the order of these n things, they should be the same. I remember something like that, but I'm not so sure about it. Let me check it again. But if you look at the table for these values, like at 1%, 11, 14, and 14, 11, they are different.
Okay. I just got confused. Yeah. Thank you.
Do you have any other questions?
No, that's all.
Okay. See you then. Maybe we won't have any recitations next week because we have 6 weeks and we don't have that much questions, that much topic right now. I guess there won't be any recitation next week. Okay. See you then.
Okay. See you.